Hi, myself Dr. Lakshmi Devi, Professor and HOD Department of ECE, St. Peter's Engineering College, Hyderabad. Now I am going to discuss under EDC subject, which is J&H second year basic subject of electronic students, electronic devices and circuits. And this, already in the last videos, already introduced the basic materials. As an extension of that, basic materials and diode characteristics and its applications. These topics we would like to discuss in today's session. Let us see the first. In the last session, basic materials were discussed. Under that basic materials, the reason for choosing semiconductors strongly defined. The same semiconductor materials we are continuing here as a recollection of its properties and its uses in electronics. A semiconductor material has an electrical conductivity value falling between that of conductor such as metallic, copper, and as an insulator such as glass. Its conductivity lies in between these conductors and insulators. That's also one of the reasons for calling this semiconductor as semiconductor. Its resistivity falls as its temperature rises. Metals are the opposite. Resistivity of these semiconductors, whenever the temperature rises, resistivity of semiconductors decreases. But in case of metals, it's an actually opposite action gets taking place. Its conducting property may be altered in useful ways by introducing impurities. Compared to the pure form of semiconductor, that's intrinsic semiconductors. Here we can increase the conductivity of semiconductor material by adding of impurities to the pure form of semiconductors. The process of adding impurities call it as doping. That's a doping process into the crystal structures. A pure form of semiconductors. When two differently doped regions exist in the same crystal, a semiconductor junction is created. Two differently doped regions. Two differently doped regions means based on the type of dopants, either it may be a pentavalent impurities or trivalent impurities, added to the pure form of semiconductors that creates by adding of pentavalent impurities n type of semiconductor, by adding of trivalent impurities p type of semiconductor. By adding these two types of semiconductors together, it creates a junction in between that. So the behavior of charge carriers, which includes electrons, ions and electron holes, at these junctions is the basis of diodes, transistors and all modern electronics exist based on the combination of this n-type and p-type of semiconductors. In general, we can define diode is a two-terminal semiconductor device and transistor is a three-terminal semiconductor device is a transistor. So that's an example here. Semiconductor materials are silicon, germanium, gallium arsenide and elements near the so-called metalloid staircase on the periodic table. We consider semiconductor materials. After silicon, gallium arsenide is the second most common semiconductor material used in laser diodes and solar cells manufacturing. Microwave frequency integrated circuits and others also we can use these two semiconductor materials. Mostly preferable semiconductor materials are silicon and gallium arsenide, but not germanium. We come to know that a reason for not using the germanium as a silicon in case of electronics components manufacturing. Silicon is a critical element for fabricating most electronic circuits. The main reason for this will be having a better controlling over the silicon semiconductor material as compared to the germanium material. The reason here you should remember, the number of charge carriers per cubic centimeter in silicon material is lesser than germanium semiconductor material. Because of a less number of charge carriers present in a silicon semiconductor material, the controlling is better as compared to the germanium. So, with that reason, silicon materials are used as basic materials of semiconductors in electronic devices. Semiconductor devices can display a range of useful properties such as passing current more easily in one direction than the other, showing variable resistances, and sensitivity to light or heat. Because here, based on increasing of temperature, it's changing its resistivity. Based on changing its resistivity, it changes its conductivity. That is easy to control the mechanism of allowing current through the semiconductor materials as compared to either insulators or conductors. Because the electrical properties of a semiconductor material can be modified by doping process, adding of impurities, or by the application of electrical fields or light. Devices made from semiconductors can be used for amplification, for switching purpose, and energy conversion purpose. These are all actually applications of the semiconductor materials. With this particular semiconductor devices of diodes, transistors, and op-amps, these are all just with this particular semiconductor materials. We can observe the switching action of diode, transistor, and amplification action of this amplification action with this bipolar junction transistors and field effect transistors. These are all the applications of the semiconductor materials. So here, as a basic concepts of semiconductors, a copper, a silicon. Here as an example of that copper is given. But in the semiconductor materials, how the bonding gets taking place, and with this particular adding of impurities such as boron and phosphorus, and which it creates actually 3 electrons a boron can consist in its outermost shell, valency shell. It consists of 3 electrons in case of boron, and phosphorus has 5 electrons. And in this, a number of electrons in outer shell, based on the number of electrons in outer shell, it can generates or creates a number of free charge carriers. Either it may be holes or electrons. If it creates a number of electrons or more, the majority carriers in that particular semiconductor are electrons, then that we named it as N type of semiconductor. If number of holes are more, then that particular framing of a semiconductor material with the doping process, we'll call it as P type of semiconductor. And this way we have N type and P type of semiconductor formations. This is just an example sake I am showing here. Periodic table of the elements. There is pentavalent elements and trivalent elements. And this pentavalent elements, here you can observe pentavalent elements as well as trivalent elements. Boron, here you can see 3A group, that is 13 column. So boron, aluminium, gallium, these are trivalent impurities. And pentavalent impurities are, that means valence shell consists of 3 electrons in case of trivalent impurities, trivalent materials, and pentavalent materials having 5 electrons in its outermost shell. Like here a nitrogen, a phosphorus, arsenic, antimony, these are all pentavalent impurities, pentavalent elements in the periodic table. By adding of these pentavalent impurities to the pure form of semiconductor, we have N type of semiconductor, and by adding of trivalent impurities to the pure form of semiconductor, this is a third A, 3A, that is the 3 elements in its outermost shell elements adding to the pure form of semiconductor. We have p-type of semiconductor. This is an example set. Might be you are observing this particular periodic table of the elements from 8th standard onwards. Let us see this p-type extra holes, how it is generated in the sense 3 valence electrons gets formed the covalent bond, and one more vacant place of that electron will consider it as a hole. These are a holes representation. So once it is combined means there is no chance to have any free electrons appears. The vacant places only will consider as a free charge carriers, which are holes here. That leads to the p-type. And here out of 5 valence electrons, 4 electrons can form nearby atoms with the covalent bond. 4 electrons are combined together. And one more electron appears to be free from its structure. That is, this blue color indicates the free electrons in it, these free electrons. That free number of free electrons increases a majority carriers. That leads to N-type semiconductor. The majority carriers in N-type semiconductor are electrons. Majority carriers in P-type semiconductor are holes. Obviously, the minority carriers are nothing but in N-type holes, in P-type electrons. And this way P and N-type of semiconductors get formed. With this combination of P and N-type of semiconductors, we enter into the semiconductor devices with the combination of P and N-type of semiconductors. Electrons at this junction gets diffused based on the carrier concentration. Electrons gets moved from its N-type of semiconductor to a P-type of semiconductor. Whenever you have placed together this P-type or N-type of semiconductors, because of opposite polarity of these holes and electrons attracted together. So while attracting, the electron can move from N-type to the P-type. Wherever the vacant place is there, that will be occupied in the P-type of semiconductor. And that vacant place in N-type of semiconductor will consider it as hole, and the filled portion is an electron. Like this, the attraction gets taking place with the opposite polarity of charge carriers. The polarity of electrons is negative, the polarity of holes are positive. Accordingly, based on opposite polarities attraction, the charge carriers gets diffused from one region to the other region. So whenever P and N-type of regions touch together, holes are majority carriers in P-type and electrons are majority carriers in N-type of semiconductor. So with this actual attraction in between the electrons and holes, here the positive, that means which loses, actually here the positive ions and negative ions are formed. That is, which donate an electron, it's actually the positive ion formed near the junction, positive ions here it's a form, and which gains the electron, that's a negative ion here. So negative ions and positive ions appears near the junction. That particular region we'll call it as a depletion region, which is free from the charge carriers. It consists of a positive and negative ions. Positive ions are N-type and negative ions are P-type of semiconductor. Whenever these two touch together, this is actually the formation of a depletion region. We'll call it as depletion region. So this is the p-n junction and conducting phenomena. If you observe and connected the two terminals with this combination of P and N type, P terminal is connected to positive polarity of the supply here and N terminal is connected to the negative polarity of the supply. With this actual phenomena of here a drifting of charge carriers without having an external supply, a drift current occurs in between P and N type of semiconductors. By applying of this external voltage here, external voltage, with this positive polarity whenever you have given to the P type and negative polarity to the N type, already the holes having a positive charge, electrons having negative charge. Because of this, the same charge carriers are repelled together. Because of that, the holes attracted towards the depletion region and electrons attracted towards the depletion region, because This negative charge repel these electrons because electrons are also having negative charge. So opposite charges attracted together, negative charges are repelled. So because of that particular phenomena, majority carriers can cross across the junction because majority carriers are more in n-type electrons in p-type holes. Because whenever the majority carriers can cross across the junction, it allows a large current to flow through the PN junction diode. That particular current will call it as a diffusion current. Because of applying of external voltage to this particular semiconductors of P and N combinations, it allows a more number of charge carriers gets diffused from one region to the other region, that to majority charge carriers, that leads to the diffusion current. So this is the basic phenomena how it allows the current to flow through the diode based on movement of charge carriers. And current always flows from higher potential to lower potential. Here the charge carriers electrons moves from n-type to the p-type, but actual conventional current will consider direction of conventional current from positive terminal to the negative terminal, that is from higher potential to the lower potential. That is conventional current. But electrons movement is in opposite to that conventional direction of current. These are the general notations of explaining PN junction diode and its movements of carriers. So let us observe here for better clarity, like anode, as usual. Anode means the positive terminal of the diode is connected to positive polarity of the supply. Negative terminal of the diode is connected to the negative polarity of the supply. In this case, how the charge carrier's movement is actually taking place, just you can observe with this particular arrow directions. Electrons are moving towards the p-type and holes are moving towards the n-type. Because of this, majority carriers can cross across the junction, which leads to the current. Current direction here it's showing current direction from p-type to the n-type. That is positive polarity to the negative polarity from this particular voltage source, positive terminal to the negative terminal. Let us see here in the PN junction, a reverse bias case. That means if we change the polarities of supply supply, like a negative terminal connected to the p-type and positive terminal connected to the n-type, what happens? Always charge carriers attracted towards the opposite polarity of a charge. That is, holes or majority carriers in case of p-type gets attracted towards the negative terminal of the supply. In n-type, majority carriers are electrons that can attracted towards the positive polarity of the supply. Because of this, the gap between the p and n-type of junction gets increases. That is, depletion region becomes wider. That is, it widens the depletion region. That is, depletion region means which is free from charge carriers. So because of that, the depletion region width gets increases in this case. Opposite polarities attracted towards the positive and negative polarities of the supply respectively. So depletion region width gets increased. Because of increasing of depletion region width in between the P and N type of semiconductor, it allows a very less amount of current. But you may be having doubt in this case. It's having minority charge carriers also, no? Yes, it's having minority charge carriers. Because of that minority charge carriers only, it allows some amount of current to pass through the junction. That particular current we'll call it as reverse saturation current. Reverse saturation current. That is, whenever the diode is reverse biased, the amount of current passing through the junction we'll call it as a reverse saturation current. Okay, that is also actually here flowing from positive polarity to the negative polarity. Just see here the current direction is positive polarity. This one is positive polarity to the negative polarity. Like this only current direction showing positive polarity to the negative polarity. That is reverse saturation. Okay, let us observe in this case a summary of this particular behavior of a PN junction diode. During conducting period and not conducting period, in what way it will respond. Just see anode of the diode, cathode of the diode connected to the positive and negative polarities of the supply respectively. Amount of current direction is also showing where I is greater than 0 in this connection of forward biased. Coming to the opposite polarities of supply, then amount of current is approximately equals to 0, but it's having some current that is negligible current that is due to reverse, that is due to minority charge carriers. We are counting that a current that is very less amount. That's why I is approximately equals to 0 we can consider. Then diode action, simply if you observe in this case, with varying of voltage source, a VD connected here, and varying of that voltage in the positive direction from its point, actually voltage waveform, characteristics if you have plotted VD versus ID, that is a voltage drop across the diode versus current flowing through the diode. With increasing of voltage after a particular voltage level, the diode allows current flows through it. Okay, that particular voltage we will call it as actually cut-in voltage of the diode. Until to reach the cut-in voltage, it won't allow current to pass through it. That particular voltage we will call it as cut-in voltage. It's based on the type of semiconductor material, the cut-in voltage gets varies. In case of silicon, the cut-in voltage lies in between 0.3 to 0.4 to 0.7, 0.4 to 0.7 volts, and cut-in voltage of germanium 0.1 to 0.3. So, cut-in voltage of germanium is lesser compared to the cut-in voltage of silicon. Already I told you the reason for cut-in voltage in case of germanium, why it is lesser compared to the silicon means the number of charge carriers per cubic centimeter in case of germanium semiconductor material, it's a large. That's the reason. By applying of a minimum voltage, it allows current to pass through it. That's why cut-in voltage of germanium is lesser than silicon. So this is an actually diode behavior based on applying of forward bias and reverse bias. It's having different applications, and operating regions, and simple diode models that approximate the actual device we can observe further in its applications point of view. So while observing the diode applications, a basic first application as a rectifier. Diode acts as a rectifier. Then diode acts as a switch. And then diode acts as a clipper and clamper. These are the applications of a diode, and different operating regions means a positive forward bias, forward bias and reverse biases. Basic regions will consider with its cut-in voltage in forward bias, and in reverse bias it allows a reverse saturation current. After crossing a particular level of varying the input voltage, a reverse breakdown occurs that we can observe in this particular behavior of a PN junction diode in its reverse bias. Let's observe background of this PN junction diode and how it allows the current flows through it. Just the drop across diode in general represented with VD, and current flowing through the diode is ID. Okay, block current flow in a specific direction. Specific direction in the sense, in case of rectifier, it allows a current flow from P region to the N region, and it opposes the current flow from N region to the P region. That is, in specific direction only it allows the current flow through it. That's the meaning. What's meant by the rectifier? Whenever it's acting as a rectifier, it converts AC to a pulsated DC. So AC means alternating current, converted into the direct current, but pure direct current we won't get at the output of the rectifier. Definitely we have a pulsated DC, which can consist of some AC components in the DC voltage. That one we'll call it as pulsated DC. Because of that, we can make use of filters at its output of rectifiers in order to minimize the pulse presence in its DC. Then we have a pure form of DC voltage at its output of filters. Okay, in case of voltage regulators and limiters, the main concept we can use. Still, if we have any such type of ripples of AC, that we can minimize with this particular voltage regulators as well as limiters. Then another application of this particular PN junction or semiconductor materials, LEDs, light emitting diodes. Okay, light emitting diodes, the basic materials you can use a gallium arsenide as semiconductor materials. Where we are using this light emitting diodes or basic optical sources in optical fiber communication. Optical sources, we have two types, that is the light emitting diodes and lasers. Okay, so light amplification, stimulated emission of radiation as a laser. These two are optical sources, and simultaneously we are having two types of light detectors at the receiver end. That is APD, avalanche photodiode, and pin diodes. These are the two different types of photo detectors and photo transmitters. That is in optical fiber communication we can use these particular LEDs. Then amplitude modulation detectors, electronic tuners, and photodiodes. Just now I told you already. These are all applications of this basic PN junction diodes. Its uses list out here. Now VI characteristics or IV characteristics will call. This already I explained with the PN junction diode how it is actually having forward bias region and reverse bias region. Once a reverse voltage, if it is crossed a particular level, then it allows heavy current to pass through it. That particular region will call it as a breakdown region. Breakdown region. Here you can observe after crossing particular reverse bias voltage level, it allows suddenly heavy current to pass through the diode. That is reverse bias, breakdown region in reverse bias. From these characteristics, I would like to calculate resistances of forward bias and resistances of reverse bias. So whenever we are calculating the resistance in the practical case, that is from its characteristics, we are going to calculate the resistances by taking the slope at 2 points, by drawing like this slope in between the 2 points of the curve. So what's the difference between these 2 points on x-axis? That is the difference between the 2 points here. The difference between these 2 points will consider as delta VR. VD, that is forward bias VD, reverse bias as VR. In the forward bias or VFIF, in general notations are VFIF for forward voltage and forward currents. VR, IRs are reverse voltage and reverse currents. Suppose if you want to calculate the forward resistances, change of voltage in forward bias, change of current in reverse bias. The ratio of VR by IR gives a dynamic resistance of the diode. A dynamic resistance of the diode that we are denoting with RD. RD is equals to delta VR by delta IR. That leads to a dynamic resistance of the diode. Similarly, at a particular point, if we have evaluated the resistance in its forward bias, that is VF by IF. That will call it as a static resistance of the diode. Static resistance in general will calculate at one point in its characteristics. Dynamic resistance, a change of 2 points, a difference between the 2 points as delta VF by delta IF leads to dynamic resistance of PN junction diode in its forward bias. Similarly, the same phenomena you can apply for the reverse bias also. Dynamic resistance as well as static resistances. So in the same way, we can calculate 4 types of resistances in forward bias, dynamic and static resistances. In its reverse bias, dynamic resistances. These are simple diode models. Ideal diode model. Here we can observe the first model as ideal diode model. there is no any cut-in voltage for ideal diode model because ideal diode doesn't consist of any internal resistance. If it, internal resistance of the diode is 0 means the drop across the diode is also 0. Immediately it starts to current flow. That's why at the 0 onwards, we can show this red color indicates an actually ideal diode current model, ideal diode characteristics model, red versus this particular. Red line gives ideal diode model characteristics. Practical diode model characteristics showing like this. Actually, practically, even though we are using the diode, these are the characteristics. Suppose if you come to the ideal diode plus voltage source model, if it is connected in series some voltage source with the diode, then definitely the forward voltage starts after crossing this particular voltage source only. Forward current starts to flow after crossing this voltage source only. That's why while varying the input, whenever it is crossing the VF, that is forward voltage, which is voltage source which is connected in series with the diode, then it starts to flow the current. In case of ideal, this is actually the red line indicates, and in case of practical, ideal diode plus voltage source model, this blue line indicates the characteristics of diode in the forward bias and reverse bias with the voltage source model. Third figure here, it indicates ideal diode plus voltage source plus resistor model. If the diode is connected in series with the series limiting resistor, then the characteristics leads to, in this case, that is red line indicates actually ideal diode plus voltage source plus resistor model only. But practical case, this the curve of a blue curve indicates the practical case. Similarly, ideal diode and practical diode, if you have any question on its characteristics, have to plot these particular characteristics and explain about these characteristics. With the voltage source model, how we have the difference. With the voltage source plus resistor model, how we have the difference. With this, I hope you are in a position to understand the simple diode model with the ideal diode and practical diode, with the voltage source model and with the source model along with a series limiting resistor. Okay, that's a summary. You can see here diodes have three operating regions, that is a forward bias. Whenever the diode is in forward bias, the diode current ID is greater than 0. Whenever the diode is in reverse bias, VD, that is voltage drop across the diode, is less than 0. Whenever it is in reverse bias, it is less than 0 means negative voltage it shows, like -1, -2, -3, -4, like that. That's the meaning of in its reverse bias, VD is less than 0. In its breakdown region, with the small change of a voltage, it allows a large current to flow through it. That is a breakdown region which occurs in its reverse bias. A red mark of characteristics indicates ideal on diode characteristics. On y-axis, on x-axis, ideal off diode characteristics totally in its forward bias and its reverse bias. In case of ideal diode usage, in its forward bias, at 0 volts itself, it allows a large current to flows through it. That's why a sudden sharp line we can observe on y-axis. Similarly, in its reverse bias, it allows 0 current, whatever may be the biasing voltage we are applying for the diode. That's why it's showing horizontal line which is on x-axis. That's the ideal on and off diode characteristics. Then ideal diode only allow current to flow in one direction. That's from anode to the cathode. Three models: ideal diode, ideal plus voltage source, ideal plus voltage source plus resistor models we already come across. In what way it's showing the difference on its characteristics of forward bias and reverse biases. Ideal diode model already explained, but here the pictures with its symbols just you can observe. Whenever this diode, if you consider current flowing through the diode is ID and Vd is the voltage drop across the diode, two possible states on and off. Diode act as short or an open depending on the bias condition. Suppose diode, if it is on forward bias, it acts as short circuit. If the diode is in reverse bias, it acts as an open circuit. If the diode is in forward bias, we'll consider it's a short circuit or a closed switch. If the diode is in reverse bias, we'll consider it as an open switch. That is, it's open. Off condition, it is in open. It's considered as open switch. In on conditions, it's a conducting in the state. Conducting means if the diode is conducting means ID should be greater than 0. If the diode is conducting means ID should be greater than 0. That particular period we'll call it as a conducting period. That is, during this particular period, on period means diode acts as a short circuit. That we are representing as a short circuit here. Okay, short circuit means in between the 2 points as a short circuit. Off condition means it is actually the blocking mode. That is, whenever if it is in the blocking mode, drop across the diode is less than 0. If it is in the blocking mode, it acts as an open circuit or open switch or off switch. Then ID is equals to 0 because current always flows in a closed loop. Whenever the closed loop breakup occurs due to non-conducting of diode presence in a circuit diagram, it acts as an open switch. It won't allow any current to pass through it. Ideally speak, ID is equals to 0, but practically speak, a reverse saturation current it allows to flow through it, but which is very negligible. Where Vd is less than 0 in that case. So this is regarding the forward bias, conducting and blocking periods of diode. And here you can observe under its different states means ideally, for all possible states of combinations based on the number of diodes it gets varies. If the circuit can consist of only one diode, it's having two states like the on state and off state. Suppose two diodes are there means each diode offers on and off states. So it gives 4 states. Similarly, based on the diode, number of diodes in the circuit, it will varies the number of states of operations in the circuit. So 3 diodes means 2 power 3, 8 states. So here you have to analyze each state by replacing the diode with the corresponding either open or short circuits. Accordingly, we can calculate the type of waveform it generates at its output and determine the state whether it is consistent or non-consistent. So, if it is in the state of consistent in the sense, the diode current ID should be greater than 0 or Vd should be less than 0. That means in on condition only we have ID is greater than 0. In off condition only we have Vd is less than 0. In that cases, either or case is satisfied, we will consider it as a consistent. If it is not the case, we will consider that as not consistent. Let us see this example. 10 volts of voltage source we have connected to the positive terminal of the diode, which is anode, and cathode terminal is connected to the resistor, that we'll call it as series limiting resistor, that is connected to the another voltage source of 2 volts. A positive terminal of voltage source is connected to the resistor. Both the negative terminals are connected together and connected to the ground. Of course, here ground is missing, but it should be connected to the ground terminal. So now we can analyze this particular circuit diagram based on input voltages of 10 volts and 2 volts. Okay, now if you observe, Anode of the diode is connected to the 10 volts of voltage source. Cathode of the diode is connected to the 2 volts of voltage source. When the diode becomes on or when the diode becomes short circuited, whenever anode voltage is greater than the cathode voltage, then the diode is in on condition. So anode voltage is 10 volts and cathode voltage is 2 volts. So in the first state, diode, that is diode 10 volts and 2 volts. In the first state of A, that is in what way we can define the voltage in the sense by applying of KVL. If the diode is open circuited and if the diode is short circuited, in what way we can calculate the output voltage and how we have a right to define whether it is consistent or not consistent. Suppose just let us observe first case. If the diode is off, okay, if diode is off means whatever may be the condition, the conditions are in general what? If the anode voltage is lesser than the cathode voltage, if the anode, please remember this point, if the anode voltage is lesser than the cathode voltage, diode is in off condition. If it is an off condition means it acts as an open circuit. If it is acts as an open circuit, then the drop across the diode is Vd to be mentioned. By applying KVL, if you write the equation, minus 10 volts plus drop across the diode as Vd plus 2 volts is equals to 0. That is, algebraic sum of voltages in a closed loop is equals to 0 is KVL, Kirchhoff voltage law. With this particular formula, definitely Vd is greater than 0. According to this formula, Vd is greater than 0 means approximately Vd is equals to 8 here, which is greater than 0. In that case, Vd is greater than 0 means we'll consider it's not consistent. It is not consistent. Okay. If anode voltage is greater than the cathode voltage, definitely diode becomes forward biased. If the diode becomes forward biased, we'll consider it's a short circuit. If it is short circuit, drop across the diode is, ideally speak, it's a 0. Practically speak, to the maximum extent, 0.7 volts is the drop across the diode in its forward bias. Okay, whatever may be the voltage, that voltage is equals to current flowing through the resistor into resistance offered by the particular current flowing through the diode into resistance offered by the diode only. So by applying ID and ID here and resistance of the diode is 1K, then minus 10 volts plus ID into 1K plus 2 is equals to 0. With this, if you have evaluated ID is equals to, you will get that is 8 by 1000. 8 by 1000 means 0.008 amps, which is greater than 0. If the ID is greater than 0, then we will consider that condition as consistent. So based on this particular analysis of examples, whether it is consistent or not consistent, you can define very easily. Either ID should be greater than 0 or Vd should be less than 0. In that cases, we will consider it as consistent, or otherwise it is not consistent. In this way, we can specify the state of diode according to the state of diode, whether it is a consistent or not consistent, to be specified at any place in the circuit diagram of the diodes. Okay, so the next application of this diode, a rectifier, a non-linear device that modifies an input voltage such that the output voltage is greater than or less than a threshold value. This is actually you can define technically a rectifier, or otherwise which converts AC to DC, AC to pulsated DC is also acceptable as a definition. Non-linear device that modifies an input voltage such that the output voltage is greater than or less than a threshold value. Now let us observe in this case half-wave rectifier that as a block given instead of showing the diodes equivalent. Input voltage is sinusoidal voltage is applied here. If the input voltage is sinusoidal is connected to the input terminal of half-wave rectifier and observe the output voltage here. Whenever the diode is in on condition, it acts as a short circuit. If it acts as a short circuit, output voltage appears to be 0. Whenever the diode is in off condition, then if it acts as an open circuit, then output follows the input. Based on the direction of diode here, positive half cycle, whenever diode is short circuit, diode is short circuited in the sense anode of the diode is positive with respect to the cathode, then output output follows the input. If it is reverse biased means in the sense output appears to be 0. In this way, if you reverse the direction of the diode connection, then this is an actually waveform. These are output voltage waveforms of half-wave. Coming to the half-wave rectifier, better way of defining the half-wave rectifier with a positive half-wave rectifier. If the input is greater than threshold, then output is equals to input. If the input is less than or equal to threshold, output equals to threshold. This is the correct way of defining the stages of rectifier. Diode rectifier circuit. This one, positive and negative, alternating current having the positive and negative notations in its input. Series limiting resistor is there, and it's connected to the cathode of the diode, and anode of the diode is connected to the negative. Ideal diode cases. Whenever input voltage, during positive half cycle, diode acts as a open circuit in this case. If it is open circuit, in what way we have output? If the diode is reversed during positive half cycle, it acts as a short circuit. So based on that, just here you can observe V out equations like in positive, Vin is positive means diode is open circuited. If Vin is negative means diode is short circuited. So if it is short circuit means on condition we are showing as short circuit, off condition of the diode we are showing as open circuit. On and off conditions, how we are defining? On means positive, anode of the diode is greater than the cathode, then it is in on condition, which leads to short circuit. In opposite case, it leads to open. That's it. Positive half-wave rectifier, a mathematical equation here we can define V out is equals to V in whenever V in is greater than 0. If Vin is less than or equals to 0, output voltage equals to 0. That's the mathematical equation of half-wave rectifier. With respect to the input waveform here, we can observe the output waveform. Only half waves it's repeating here. Positive half cycles only repeating. Negative half cycle is totally clipped off. That is totally erasable. Because diode is in negative half cycle, it's an open circuit, then output voltage is 0. Based on the diode connections here, you can have positive half cycle or negative half cycles. In the non-ideal diode cases, how does a non-ideal diode change the behavior of the circuit? Include the forward voltage drop Vf by modeling the diode as an ideal diode in series with a voltage source. Suppose if you have such a critical issue, if the voltage source is in series connected to the diode, definitely the functionality of this voltage source to be considered on switching action of these diodes. How it will be observed in this. Now the diode is connected in series with the voltage source of Vf. That is negative terminal of Vf is connected to the anode. And as usual, Vin is connected to the cathode. That means in this particular circuit diagram, when the diode is in on condition, when the diode is in off condition, if you analyze this, you come to know that functionality of diode and its effects showing on its output. Whenever Vin is greater than minus Vf. Vin is greater than minus Vf means, because why we are considering it's a minus Vf? Negative terminal is connected to the anode. That's the reason a minus Vf we are denoting. If Vin is greater than minus Vf, in the sense during positive half cycle and in the negative half cycle also, if the Vf is, suppose let us consider Vf is equals to 2 volts, like minus 2 volts. Until to have minus 2 volts in its sinusoidal waveform, diode is in open circuit only. Diode is in off condition only. If the diode is in off condition, it acts as a open switch here. Just you can observe this one is open. It is open means this output voltage just followed the input waveform. Okay, now whenever the second stage here you can observe Vin is less than minus Vf. Suppose Vf we will consider 2 volts until minus 2 volts. If Vin is less than minus 2 volts, like minus 2.1, 2.2, minus 3, minus 4, minus 5, then again minus 5 to again it is minus 3, minus 4, minus 3, then minus 2, minus 1 and 0 in the negative half cycle. So whenever Vin is less than minus 2 volts, then diode becomes forward biased. If the diode becomes forward biased, it acts as a closed switch. Because of this, it's a closing. If it is closing means output voltage is same as this forward, Vf, a voltage source voltage only. That is output voltage is equals to the Vf. Okay, this is in general we'll consider because of its internal resistance of the diode, it's having its own voltage drop across this diode if it is in forward biased. That's the meaning of denoting this voltage as forward biased voltage of the diode as Vf. Okay, that is suppose if you consider 2 volt. In general the diode whenever it is in forward biased, the drop across the diode is 0.7 volts only. In this case, external voltage if you have connected, that shows as an output voltage. Let us observe in this case, Vin is greater than minus Vf. Output follows the same as input up to here. Whenever Vin is less than or equals to minus Vf, output is minus Vf. That is, this green line indicates the output voltage waveform and yellow line indicates the input voltage waveform. I think now we are in a position to understand the functionality of the diode based on voltage. Okay, so next lesson we will see after completion of this half wave rectifier, then we'll go for the full wave rectifier and observe the behavior of this full wave rectifier with the sinusoidal inputs and analyze the diode acts as a full wave rectifier, and then we'll go for the derivatives of this half wave and full wave rectifiers and its parameter calculations. All these things we can observe in the full wave rectifier. Just here before going to the full wave rectifier in the next video, this one is a sinusoidal input voltage if you have given as an input to the full wave rectifier as a block representation. Output voltage waveforms, it depends on the direction of diodes connected in the circuit. We are having either positive peaks, positive half cycles of the waveform or negative half cycles of the waveform based on the diode connections. Either or these types of output voltage waveforms we are having in full wave rectifier. The difference between the half wave and full waveform, it gets repeated in the full wave rectifier as output, but in half wave, half of the waveform appears at its output. So with this, I am concluding now this rectifiers. I'll extend the rectifiers discussion with the full wave rectifier in the next video. Thank you.